Okay, so this is problem 27 on the chapter 7 homework of rotational motion and the law of gravity. So the first thing I did was draw a diagram based on what we knew. So we knew that the Ferris wheel was 18 meters in diameter, which means 9-meter radius, and it revolves at 4 revolutions per minute. So the first sub-question asks for the centripetal acceleration, and we know that the formula is v squared over r. And then we know that the formula for v equals r omega. Excuse me. So we can substitute v with r omega, and here I just distributed the square, and I changed this into our desired format by making this radians per second. As you can see, right now it's revolutions per minute. I just multiplied 1 minute in 60 seconds and 2 pi radians in 1 revolution, and I got 0.42 radians per second. So I just substituted the radius, which is 9 meters, and our converted omega, which is 0.42 radians per second, and divided it by a radius, and I got 1.58 meters per second squared. So we know that that is our centripetal acceleration. Now the next question asks for what is the force that the seat exerts on the bottom. So if you look at the sum of all forces, you know that the force of the bottom must be equal to when subtracted by the weight of the entire person and object, should be mass times the acceleration. And so if I move the mg to the other side, F bottom equals mg plus mass times acceleration. And if you think about it this way, because the force of the bottom, the force of the seat pushes up, and mg pushes down, it should be equal to the mass of the object and the centripetal acceleration. So you can take out the m, do a reverse distribution, and you just substitute the known values. So 40 kilograms times the force of gravity plus the acceleration that we found in part A, and we get 455 newtons up. And part C asks for the force at the top. So the force at the top minus mg equals m times negative centripetal acceleration, because now the acceleration is going downward. So the normal force of the seat pushes up, mg pushes downward, and the centripetal acceleration is downward now because he's now at the top. So we can move mg over to this side. So F top equals mg plus m times negative centripetal acceleration, and you can do the reverse distribution of that again, m times gravity minus centripetal acceleration, and you substitute the known values, and you get 328.82 newtons up. Finally, halfway. So if you think about it from a coordinate plane point of view, you know that when it's halfway, the centripetal acceleration has nothing to do with the force that the seat supplies up, because it is exactly perpendicular to the force of the seat. So the only two forces that are acting upon this position of the person are the force of gravity, mg, and the force of the seat itself. And because the person is not moving at that point, the force of the seat halfway must equal the force of gravity. So F halfway equals mg, and you substitute the known value of m, 40 kilograms, gravity 9.8 meters per second squared, and you get 392 newtons. So yeah, that is how you do problem 27.